What is this music from? Oh, my older brother made it. Ah. He's a trumpet player. He's really good at the trumpet. Hey, Adam. Adam all together. Oh, Anonymous Cowboy. How's it going? Hope semester's going well for you. Here, how about this? There you go. Little raffle gift before the stream. Random VIP. Hey Vixen, how's it going? Good. Oh, where's? Okay. Let's get this. Wait, what happened to the iPad? That's weird. Okay. Play this music. Okay. That's right, Vixen. I used to put quotes from students. Those are actually all student quotes. And then I stopped doing it because I don't actually do it, and it's my little brother who does everything, and he has more important things to do. So. Yo, Vechihan, how's it going? Femvox fan, welcome. All right, students. Let me go check out Discord in case anything's happening there. Nothing. Crickets, as usual. Okay, students, you have homework due on Sunday. Very light homework compared to the homework that's about to happen next week. And in the book, we're finishing chapter 3 and starting chapter 4. Look at this. With my laser, I can encircle things. See that? Okay, so read the book. It's fantastic. Modulo the error in the proof of the fundamental theorem of algebra. Okay, no one's perfect. Except for me. All right. No T-Pain music anymore. Yeah, that didn't last very long. Yeah. Good. Yeah, that's not. Yeah, we're going back to this stuff. Okay. So today I'll begin by reviewing stuff from last semester. Gauss's lemma. How do you tell whether a polynomial is irreducible or not? We're gonna need to know that, and we'll see why we need to know that soon enough. Okay, and I'll review the basically 2 tricks that we know, and then we begin the real task at hand, which is the study of field extensions. Field extensions is just the abstractification of the evolution of numbers, the gradual systematic introduction of new numbers to an old number system. That's what the concept of a field extension captures. And so I want to go back every time this happens to the 3 sentences of Galois theory. And look at the first one right there. See, this is now going to start to become more, it's going to start illuminating. Okay, every time a new number is introduced, you get something called a field extension. We're going to learn what that word means. Very simple idea. Those are field extensions are the basic objects of study in Galois theory. And then I'll just do some examples of field extensions to get our hands dirty. All right, so Gauss's lemma. Let's start. This is going to be more like review. Gauss's lemma. What does Gauss's lemma fundamentally say? It compares irreducibility of a polynomial over the integers versus over the rational numbers. So the setting is this. Suppose you've got a polynomial. Yeah. With integer coefficients, which you know to be irreducible. Which means can't be factored into a product of non-units. That's the general definition of irreducibility of an element in a ring. The question that Gauss's lemma just once and for all answers is, well, that means that you can't factor it as two integer polynomials times each other. But can you factor it if you allow yourself rational coefficients, fraction coefficients? And Gauss says no. Here's Gauss's lemma, stated in my style of teaching. Okay, so this is the lemma. Lemma 4.3.2. Okay? No. All right, so that's great. If you want to know if the rational numbers are going to help you factor this polynomial, they won't. Irreducible over Z implies irreducible over Q. That's the slogan. All right? And now I refer to you to your notes from your note cards from last semester. We proved Gauss's lemma. We used this idea of the content of a polynomial and that the content multiplies and so on. And it's a simple proof and we did it. Okay, so that's the point. That's all I want to sort of jog your memory here from last semester. I'm not going to repeat last semester. Okay, so it's nice. It's a good curiosity to think about. And the lemma says, yeah, passing to rational numbers isn't going to help. But passing to more complicated numbers can help. For instance, passing to more complicated numbers can, and in fact, in a sense, will always help. Okay? Yeah, that's a good, yeah, Vechihan, write this lemma down. No. Okay, passing to more complicated numbers can help. Will, in a sense. Will help. Because see, look, if you have this polynomial, this is irreducible over Z. How do you check whether a quadratic polynomial is irreducible? You have to check, just try to multiply two linear factors and equate coefficients. You can just do it by hand. Or, yeah. Okay? Same with cubic. You can kind of do it by hand by saying it's got to have a linear and a quadratic and then try to match coefficients. All right, so this is irreducible over Z. This one doesn't factor. Oh, sorry. We're letting t be our variables in this class. T squared minus 2. But now, if you allow yourself to work in the following field, Now, why is this a field? Okay, we'll get back to this. That's the next topic. These kinds of questions are going to be facing us straight here. Okay. So anyway, this is a field. If you allow yourself these kinds of numbers, then of course this thing factors. Okay. This is all right, so Gauss's lemma is just talking about the relationship between Z and Q, and not Z and any other field. Okay, awesome. Next, how do you actually tell whether a polynomial is irreducible? Here's a question. The next topic. And let's just make it simplest. Let's say over Z. Okay? This is kind of impossibly hard problem. In general, good luck. Good luck. Because after all, individual integers are stupid polynomials. So this is also asking, like, how do you know whether a random integer is a prime number? And if you know anything about that, you know that it's kind of like just people will say a bunch of stuff and say, look, we have this and that test, but there's no definitive, golden silver bullet. All right, it's hard. Millions of years of trying and partial results. All right, that's just a constant polynomial. And now we're asking how do you know whether a big old polynomial is irreducible? So this is going to be a hard problem. But we have two tricks. Two tricks. Of course, the first is I bet you read it from a table of irreducible polynomials. Okay, good. Hi, pandemic. How's it going? Okay. First trick. Very used a lot. Okay. Eisenstein's criterion. Which we proved last semester. In a sense, we're kind of very prepared for Galois theory, all right? But it's good to see things twice, just visually. All right, Eisenstein's criterion, let me state it, okay? So you have yourself a polynomial, like this. Wow. Look at that polynomial. Here's our polynomial. Okay? Now, if there is a prime number such that let's list the criteria such that P divides all the numbers except the top coefficient. P does not divide an. So all of these are multiples of the prime, and this one's not. Okay, you can't have P dividing everything, okay? P does not divide an. That's the first thing. And two, P squared does not divide a0. So it's not 2 divisible by P. P squared does not divide a0, then that polynomial is irreducible. All right. So that's a powerful little trick theorem, criterion to that we'll use a lot. Okay, that's often available in the examples that we'll study. Okay, but you should know that if someone just slaps a random polynomial on the page, you know, it might still be irreducible even though it doesn't fit Eisenstein's criterion for any prime. That can happen. Yeah, that can happen. Let me show you an example. Let me show you an example of such a polynomial, which should jog the memory should come back. The pth cyclotomic polynomial. Cyclotomoic. I'm going to keep that. Pth cyclotomoic polynomial. It's so beautiful. You want to see it? It's this. P is a prime. Okay? It's this. Wow. What a gorgeous polynomial. Okay? This polynomial is irreducible, famously. Now, if you go back to your notes from that particular note card on Eisenstein criterion and irreducibility of polynomials, the way we prove this is through Eisenstein's criterion, but after a substitution. Okay? We did a clever little manipulation, which you should remember forever in your life. The beautiful manipulation. This is, by the way, the first thing to do is to write it like this, because that's true. This is a true thing I just wrote. And then do a substitution, which is t equals u plus 1. And then pass to that other polynomial with u plus 1 in for t, and use the fact that p choose k, the binomial coefficient with p on top, these things are divisible by p, as long as you don't do the outside ones. Is a multiple of p. Or k. Yeah. Okay, so you use, that's the trick. But it is irreducible using Eisenstein after a change of variables. But look at it on the nose. I mean, you're not going to find any prime that divides everything except, yeah. So don't think that this is some kind of if and only if type statement. Okay, great. Okay. Eisenstein, that's the one that you should remember forever. Okay, there's another trick. Okay, another trick. I would not really call this a trick, but it's just an idea to always have. Okay, an idea to always have ready in any kind of number integer situation. It's to reduce mod any integer you'd like, but typically a prime. Okay, reduce modulo a prime. So the point is, we have a ring homomorphism. Okay. In this class, I'm going to start writing z mod pz as fp, because it is a field after all. And let me emphasize, I just want to emphasize that. We have this reduction map, which takes a polynomial and sends it to reduce the coefficients. Okay. And just slap that polynomial down. How long did it grow hair? I was born like this. Okay. All right. Okay, so now what you do is the following simple observation. If f factors over z, then it's got a factor over fp. So if you figure out that it doesn't factor over fp, then you can reverse figure out that it was irreducible. Okay, so you can flip this observation around. So flip it around, and you get a trick. This trick is less of a trick, I would say, because if your polynomial does factor mod 3, say, or something, it actually doesn't tell you anything about the original polynomial, whether it factors or not. Okay? So then the issue is, how do you find a useful prime to mod out by? It's kind of not at all obvious, at least not to me. All right? And let me show you an example that's from the book. For example, did you know that this is irreducible? Oh, why did we assume? Yeah. I think p squared will be false in general. Yeah, p squared will be false. Yeah. No. In the proof of Eisenstein, you will use p as a prime if you look at the proof. You'll use the fact that, oh, p divides one of two things. And so p goes into one or the other. You're going to use that. Yeah. I remember. Yeah. Go look at the proof again and see where the primeness sneaks in. Yeah. What does irreducible mean? Irreducible means not the product of two elements which are not just like plus minus 1. Okay? Those are called elements like plus minus 1 don't count as factoring. You know, you can't. 13 is 1 times 13. That doesn't count as factoring, my friend. Yes. So non-unit is the word. So, okay. Oh, is this? Hey, did you know this is irreducible? By the way, we're talking about factoring with integer coefficients, which by Gauss's lemma is the same as trying to factor with rational coefficients. You're not going to get any new mileage from passing to Q. Okay, reduce modulo 5. And you get this thing. F of t is congruent to t to the 4th plus just 2. Okay? Or if you'd like, the reduction mod 5, f bar if you'd like to call it that, is t to the 4th plus 2 in this ring, in this polynomial ring. And now, it turns out by amazing luck that t to the 4th plus 2 is irreducible. Okay. You might say, well, you're just in a new, you're going in circles here. But the circle's getting smaller because to check whether this is irreducible is, in principle, a finite check. Because look, the two factors are going to be linear, either linear times whatever, cubic, or quadratic times quadratic. And in each case, there's only 3 coefficients in each one, or 2, and yeah. And the coefficients are in a finite set, F5. So there's just, 5 to the 10 trillion possibilities that you have to check. 10 trillion is some number. Yeah? So it's better. It's better. So what you do basically here is you check it all. Check it all. There's a smart way to check it all by the degree, and then kind of limiting how much you actually have to check. But you can check it. And you get no possibilities. All right? Good. Awesome. So that means that originally your polynomial had no chance of factoring into 2 smaller degree polynomials. Awesome. Okay, so that's how you use that trick, reduction mod p. And as the book points out, hold on, if you tried to reduce mod 3, then t to the 4 plus 2 does factor in F3 adjoint t. In fact, there's actually a beautiful kind of story in number theory which asks a question of the following form. If you're given a polynomial, like this one, over the integers, at which primes, when you mod out, will it remain irreducible? And at which primes will it split in a certain, maybe quadratic, or etc.? Investigate the collection of primes where it stays irreducible or it splits. And the answer to that is, it's complicated, but beautiful. Okay? So that's a beginning of a long thread. All right, good. So those are the tricks we have. Those are the tricks. Done. Polynomial review. Okay. Can you always reduce and then check? Yes. If a polynomial is irreducible over Z, then it is a hard theorem called Hilbert's irreducibility theorem that there will be infinitely many prime numbers modulo which the polynomial stays irreducible. But it's not constructive. So yes, there will be a prime that tells you good news if the polynomial is indeed irreducible. But which prime it is just this. Who knows? Hilbert's irreducibility theorem. That's what you want to go look up. A marvelous result. No. Eisenstein's criteria is very much about being in a particular kind of ring like Z and not over a field. So Eisenstein will not even be parse over FP or over F. Yeah, you got it. Eisenstein uses the integers very fundamentally. Okay. It's yes, procrastinate. It's not just one prime. In fact, you can assign a notion of density of a set of primes, and the density of primes for which it stays irreducible is very big. It's 1, something like that. Positive. There's a difference between positive. Good. Positive. That's positive. It's not 1, it's positive. So it's like a proportion. All right. Next, I can't, okay. Very good questions. This is why I like Twitch, because just random people ask really good questions. I mean, they're math people, I can tell, but whatever. Or they're family members. One of the two. Okay, let's keep going with class. This is a class, folks. Field extensions. Subject of the rest of the semester. Okay, let me say what a field extension is. Okay, Usually, okay, first you gotta know what a field is. You gotta know what this means. Means it's a ring where everything outside of 0 is invertible, multiplicative inverse. You can divide. All right? If you have a field, and you have another field, then you can ask, are these two fields related in some way? And the way we express relationships in algebra is through ring homomorphisms. So suppose you have a ring, I want to tell you something about fields and why they're so great. Suppose you have a ring homomorphism. Between two fields. Then it has to be injective. After all, we know that the element 1 has to go to the element 1, and that in a field, by declaration, 1 is not equal to 0. So the 0 ring, the wrong, is not a field. Okay, so 1 doesn't equal 0, by the way, a field. Okay, so we know that this homomorphism can't be the 0 homomorphism. Not everything goes to 0. But on the other hand, suppose some non-zero element did get sent to 0. Suppose some element went to 0. That would be a failure of injectivity. Right? I'm checking the kernel. I'm looking at the kernel of this homomorphism. Okay, suppose it went to 0, then what? Then look. The inverse of k exists. We're in a field. This thing is 0 times blah, which is 0. But on the other hand, ring homomorphism or field homomorphism says this is the map applied to the element 1. And so 1 went to 0. Not allowed. Bad. Which means good. Meaning it's injective. So every time, and notice that what really didn't what mattered was that the target ring, this being a field wasn't what mattered. It's just that the domain was a field, K. That's all that mattered in this argument. So whenever you have a homomorphism out of a field, okay, let's say to another field, it's automatically injective. There's no kernel, there's no squashing a field to a smaller field. It's always, in a sense, an inclusion type map, an isomorphism onto its image. All right? So when you relate two fields by a homomorphism, you are essentially saying that the domain field can be viewed as a subset faithfully in the target field. So that's why the book will use the word monomorphism of fields. Why is the book always saying monomorphism? Monomorphism is the UK, I guess, way of saying one-to-one, injection. And the reason it's coming up is that's the only kind of maps that a field affords to other rings. It's beautiful. Such simplification. All right? Good. So, monomorphisms of fields. That's what language you'll see a lot in the book. All right, so now I'll tell you what a field extension is. There's actually two sort of competing notions in the book. The one of them, I'll tell you from experience, is the one that everyone thinks of when they think of the word field extension. Number one, like the abstract version. Ready? A field L is an extension of a field K. I'm going to use the word abstract, okay? Just to divorce these two concepts. If there exists a monomorphism, which just means a homomorphism, and we call the entire function, this is we're going to call it an abstract extension of fields. And hopefully, which one I mean will be clear in context, but always ask. Or just wait for the context to clear up. Okay? Good. Oh, okay, that's the abstract way. There's also the embedded or concrete way, which is what I'll call it, okay? There's the embedded / concrete version. / the version that, if you asked a random mathematician, this is the definition they'll come up with. All right? A field L is an extension of a field K. If ring monomorphism is redundant, ring monomorphism? No, I guess not, because you could have monomorphisms of groups in vector spaces. Yeah, so we want it to be a ring monomorph, a field, a homomorphism of fields. Okay, good. Yes, homomorphism of fields. Great. Good. So a field L is an extension of a field K if, drumroll, K is a subfield of L. And this is the one that really is what's in people's heads, okay? Notice that this is an instance of the previous one. If you think about the inclusion map as a homomorphism, which it is. And that's why I kind of think of every one of these as a sort of inclusion map. Okay, let me show some examples of field extensions. Field extensions. Let's just forget that distinction for now. Because for us, for the first part of the class, all of our fields are in one big ambient home, C. All of our numbers, which we think of, are just complex numbers of a certain type. And then we look at certain subfields of that large complex number field, and that's what we're going to study. So let me show you an example of a field extension. Way at the bottom here is Q. And we'll get back to why it's at the bottom. Why every field in C has to contain Q. It's easy. All right, so you got Q, and here's an example of a field extension. You know what Q adjoin square root of 2 means as a set. A plus B square root of 2's. A and B are in rational numbers. Okay? Here's another one. A plus bi's, where a and b are rational numbers. Here's another one. Now, we should talk about this one. We should talk about this one just for a second. In the homework, you have to prove that this thing is actually a field. Now, I need to remind you what this thing means. When we write this parentheses notation, this means the set of numbers of the following form. The cube root of 2 all squared, which is the cube root of 4. Not obvious. Not at all obvious. Why is it a field? Okay, so this is my K in these examples, and this might be an L, or this might be an L, or this might be an L. All right? Field extension. Concrete field extensions. Okay? Tried puzzling over this and it simply got too messy. Hint? Okay, the hint is linear algebra. Try some linear algebraic arguments. Okay? Just a hint. Okay, well, but we will see, after you struggle with this one, we will see the power of abstract commutative algebra. Okay, wait, what did I, C times the cube root of 4. Yes, that's right, that's right. Meaning the cube root of 2 all squared. Cube root of 4. No. Okay. Hey, you want to see another field extension? Check out this one. It's called this. Square root of 2 and square root of 3. Now let me explain what this field is. And then we'll understand the third thing that I wanted to say today, but didn't quite get to. All right? All right. Okay. So, third thing. You might be tempted, if you're very new to this subject, you might be tempted, oh, what he means when he says square root of 2 and square root of 3, you add those new numbers in to Q. Add these two numbers in, toss them in with Q. What you mean is, A plus B square root of 2 plus C square root of 3. And this is wrong. It's wrong for kind of an obvious reason, but if you still think about it, it's not totally obvious. That if you give me square root of 2 and square root of 3 to create a new number system, you have to also give the square root of 6, because that's the product of the two. And a field has product, closed under production, producting, multiplication. So you gotta at least have the square root of 6 in there. And so you toss that in too. So what this actually is, so pay attention. What this actually is, and when you see these things, you need to start asking, wait, how does he know this in general? What's gonna happen when I just start tossing any number of elements together? Can I sort of tease out the structure of this field that you'll get? How do I anticipate systematically that this is the case? Because apparently I stopped here and I'm saying this is a field. This is apparently a field. Okay, so that's not obvious. That's not at all obvious. But another question emerges, which is, hold on. When you said you needed to toss the square root of 6 in, how do you know that it's not secretly already in there? Oh, spin off. Wait, hold up. How do I know? Just phrase it in terms of linear algebra. How do you know that the number 1, the number square root of 2, the number square root of 3, and the number square root of 6, those 4 numbers are linearly independent over Q? How do you know they're linearly independent over Q? Little puzzle. Okay, so I'm going to go through that puzzle real fast for you right now. Okay, so why? In other words, can this be like this? And now look, here's something you can do. Good job, Lilac. No one's seen that joke. Great, awesome. All right, how do you know this? Okay. Multiply both sides by the square root of 6. Maybe there's a faster way. Some genius can tell me. Okay, multiply both sides by the square root of 6. Okay, 6 equals a square root of 6 plus b square root of 12. Wait, did I make a mistake? I think I made a mistake. Okay, but maybe first square it. No. Okay, you guys will have to help me. I think I just discovered a mistake in my... Okay, fine. Do this. I'm being stupid. Okay, does this help? Hold on. Wait. Hold on. Multiply by... Wait, square it? Okay. Alright, let me see what I did wrong here. Yeah, square both sides. Maybe square both sides. Technical difficulty. Kappa, you're right. Hold on. I thought squaring both sides didn't get me anywhere. Okay. Let me square both sides. Let me go back. That was good. 6 equals a squared plus 2b squared plus 3c squared. Now, okay, well, we're gonna do it. F it, we'll do it live. Okay, 2 times... Yeah, I know. Yeah, spring bottom, good. Now, but how? Okay. Oh my lord. Okay, we'll do it. Yeah, clearly I made a mistake in my easier way. Okay, we're gonna do this now. Okay, so what spring bottom is saying, helpfully, is you know this is true. And you want to solve for... Is that easier, spring bottom? Multiplying by square root of 6? Is it easier? It might be... Oh, it might be easier. Yeah, it's better. Okay, good. Pandemic, you saved me. So squaring, I wanted to avoid. Good. Great. Good, good, good. So yeah, let's go back and multiply by square root of 6. All right, this is better. This is friendlier. I didn't want to... Okay. B times the square root of 12 is 2b square root of 3 plus c times the square root of 18. C times the square root of 18. Pandemic watch. Yes, it's a green check. C times the square root of 18 is 3c square root of 3. Ah, interesting. Okay. And then they want to resubstitute 3 times the square root of 2. Good job. Yes. And they want to resubstitute this in here. Okay, so a times Okay. Yes. Good. No. This was just me making a stupid mistake last time. Before class. 5 minutes before class. Okay, good. Now, we collect like terms. Okay, you collect like terms. Okay, look at these like terms, folks. Oh my god. Yeah, thank you for following right when I'm struggling. I get, yes, good. AB plus 3C. Okay, all right, good. Collect like terms. AC plus 2B. Equals 6. Right. And now you take the rational stuff onto one side and then you square again. Amazing. Okay, so okay. Okay, good. Okay, wonderful. Okay, so very good learning experience. Now, notice you gotta square again. Square again. Look what you're gonna get. Two AB, or you know, two. Okay, and so then look what's rational and look what's irrational. So what the only thing I'm going to appeal to is that the square root of 6 is irrational. If you want a proof, you can use the same argument that shows the square root of 2 is irrational by divisibility of a fraction, numerator denominator type. All right, so square root of 6 is irrational. And so the only way this can happen is if the thing multiplying has to be 0. Okay? So then you extract out that one of these two factors is 0. Because we're over Q as a field. So this might be 0. And then you have to go back and you see that this is right here. So this is 0. But the square root of 3 is also irrational. And so it forces this other one to be 0 too. But then the right-hand side over here is 0. And you get this is 0. But a is a rational number, and square root of 6 is irrational. So you get a contradiction. You couldn't have a, b, and c rational numbers making this equality work. So the square root of 6 is a new irrationality that comes even if you adjoin just square root of 2 and square root of 3. You cannot get square root of 6 from rational combinations of square root of 2 and square root of 3 additive. You have to add it in as a new number. But then the mystery is, second mystery is, why is that the end? How can you say for sure that you obtain a field? So division is exists. All right. So thank you chat for saving my blunder there. Stupid blunder. Okay, but look how much pain this causes. And so we should try to this will help us appreciate the more general theorems about field extensions, especially field extensions which are like this, where you add a square root and another one, and then another one, and you can confidently say how many, exactly how many new numbers you've introduced. All right, so that's something called the theorem on natural irrationalities, I believe, is where this this particular conversation leads. The theorem on natural irrationalities. Okay. Good. Great. So I didn't get to the last part. I just showed you some examples of field extensions. Let me just reiterate this second one that I just did. This is an example of a field extension that you might never have thought about. Here is now K, and here is L. Okay? So that's, and the subject is about the constellation of field extensions that, in the beginning, for us, concretely, are all sitting inside the complex numbers. All right? What is the fine, detailed structure of the constellation of field extensions within the complex numbers, say? And what kinds of mathematical data can we attach to a field extension? Go back to the 3 sentences of Galois theory. To every field extension, we attach, in particular, a group. That'll come later. Before we do that, we'll attach an integer called the degree. It's a measure of the size of the field extension. That's the next order of business, really, coming up next week. All right? We'll measure how far the subfield is from the big field, just with an integer. Okay, so that's next week. And just from that measurement device, we'll be able to deduce some rather marvelous things. So next week already the treats begin. Is there a general algorithm for checking independence over Q? I don't know. Actually, hold on. Actually, no, I don't know. Okay, you could say square root of 6 isn't in the subspace when you consider R as a, yeah, the new field as a Q vector space. Exactly, Kappa. Exactly. Exactly. And we will start using this language of vector space over field next week. Exactly that, Kappa. Okay. All right, Femvox. Okay. Oh, Femvox is saying some great compliments. That means, we know what that means, right? What does that mean, class? Why would someone near the end of the stream just shower us with praise? What does that indicate? Just Psychology 101. What's the underlying reason? It's endorphin time. It's dopamine time. Exactly, Lilac. It is time for serotonin. It is time for the Kappa. Yes, exactly. Exactly. Okay, I don't think any. Hey, followers, thank you. Easy Fence, Boot, Atch, Agony. Wow, so many that I missed. Well, 4, not that many. Okay, whatever. Okay, so credits. Ready? So Femvox, number 1, first in line. But then there's also usual suspects like Vixen, and then of course there's Kappa. Wonderful member of the community. Comes to class more than my students do. Maybe. Not really, actually. Because all my students actually come to class. I've been noticing all 4 of you come into class. I see another in the Discord. I see, okay, I don't want to say your name, but I see you. RDL, maybe? No, that doesn't make sense. Someone. I see you. All my students. Remember, Sunday, homework's due, and I'm gonna hit you with a true and false quiz, like I did last semester. That fun begins. If you wanna get a heads up, look at the true-false questions at the end of chapter 1. I'll try to like do spin-offs or something. Okay? Good. I'm gonna try to trick you though. I'm gonna try to trick you. All right. Femvox, Vixen. We're gonna have a fun semester. Kappa, all my students. Who else is here? Blowfish? Okay, who else? Who else is last minute? Surfing Coder. Okay, yep. Surfing Coder. Yep. Yeah. Who else is here? Oh, Lilac shows up. I mean, Lilac was here the whole time, so Lilac. Okay. All right, who's just here for the... Oh, Springbottom saved me. VIP, man. VIP. Springbottom. Springbottom saved me from squaring. I really didn't want to square. Nice. Saved. Saved from squaring. But we had to square anyway at the end, but whatever. It's hey, class. I want you to pay attention to something here. Okay? Notice that fundamentally, kind of fundamentally, we had to square notice how like at the end of the day, the total like degree of the stuff, the algebra that came out was 4. There's a 4 here. Just anyway, So let's see, what else? Kappa saved. Femvox. Okay, there's basically 5 people. Pandemic saved us too. Pandemic saved. VIPs. Pandemic. Did you save me? I think you saved me at some point. Nice method. Oh, yeah. That counts. Procrastedigitation. What a smart person. All right, and there's no mods. We were you guys were on your best behavior, so no mods had to come in and lay down the law. Mantez. Yes. Is that sarcasm? I can never tell with this community. All right, Vixen. Soon to be. Okay, you want it? Okay, fine. We'll do it. You know what? My students deserve to be on the top. My allegiance is to my students. There you have it. To the top. All right, credits. Oh, look who shows up. Pale blue zebra. Right at the end. All right, folks. Thanks for keeping this place running. You guys saved me from my algebra error, where I'm... You know what I did? I won't even tell you. It's embarrassing. But you saved me. You got me through that god-awful mess. That was incredible. This was... all credit goes to the community here. So... we're starting to learn field extensions. It's the apparatus that expresses the concept of new numbers relative to old numbers. The field K, the subfield, is to be thought of as the old numbers we had. And the field L is to be thought of as the new numbers. And when I say numbers, I mean a number system where division is included. Field. All right? So we have lots of mysteries ahead of us. Like, how do I know that a set of numbers I just slap on the page? Oh, it's A plus B blank. We'll see that. How do I know it's a freaking field? So far, do your homework. Seems like a real pain. So pay attention to that pain and then appreciate the general ring theory that's about to show up. Okay. Hey, Okneblap. See you next time. You didn't quite make it in the credits this time? Okay, you did. Fine. Okay. Okay. I'm feeling good. Okay? Okay, fine. All right. AC. But don't you have to, like, you just came back from teaching. Oh, nobody here. There's a AC is here. Ran from their class and went straight to the computer to watch the end of Galois theory, the dopamine part. Welcome, AC. About to leave here. All right, folks. I gotta go learn commutative algebra. I've got to learn commutative algebra. Okay. Thank you. It was actually refreshing to watch the algebra struggle. No lie. So, what's that? What does that say about you? Like, what does that say?